You ever wonder how an AI, like ChatGPT, can just spit out a whole paragraph in seconds? Well, it's not magic, not really. It's a super clever process called autoregressive inference. Today, we're going to pull back that curtain and look at the engineering tricks that make this incredible speed possible and why it's so important for the future of AI.
Okay, so let's just dive right in. On the surface, it seems simple, right? The AI just adds one word after another. But as you're about to see, generating text this way is actually a huge computational puzzle. How in the world does the model keep track of everything it's already said and do it efficiently? To really get our heads around this puzzle, let's use an analogy. Imagine our AI is a royal storyteller, and their job is to compose this grand, epic tale for a king. But here's the catch. This king has the absolute worst memory in the entire kingdom. Just think about how maddening that would be. To add one single word, our storyteller has to go all the way back to once upon a time and start over, every single time. Well, this is exactly how a basic text generation model works. It has to reread and reprocess everything it's already written just to figure out what the next word should be.
Now, this whole step-by-step process has a pretty technical name, autoregressive generation. If you break it down, auto means self and regressive means looking back. So the AI is literally looking back at itself to figure out what comes next, one little piece at a time.
So here's what that looks like in practice. To get the word sat, the model looks at the cat. Easy enough. But for the next word, on, it can't just look at sat. Nope. It has to go back and reprocess the entire phrase, the cat sat. You can see the problem, right? This mountain of repeated work just grows and grows with every new word. It's incredibly slow.
And here's the real kicker, this method just doesn't scale. The amount of work, the computational cost, it explodes. Trying to generate a whole paragraph would be painfully slow. A full page? You can forget about it. Our poor storyteller and our computers would just be completely exhausted. There has to be a better way.
So how do we fix this mess? Well, let's go back to our storyteller. What if they didn't have to rely on the king's terrible memory? What if they had, say, a magical scroll that remembered the story perfectly up to that point?
This magical scroll, it has a real-world name, KV caching. You can think of the keys and values as a kind of shorthand, like the Cliff's Notes for the story so far. It captures all the important concepts and relationships. By storing this shorthand in a cache or memory, the model can just glance at it instead of rereading the entire epic. All its brain power can focus on just one thing, figuring out the very next word.
I mean, the difference here is just night and day. The forgetful storyteller is trapped in this endless loop, but the one with the magical scroll, our KV cache, is lightning fast and efficient. It's a brilliant trade. We use a little bit of memory to hold the scroll, and in return, we get a massive reduction in the work the computer has to do.
And hey, don't just take my word for it. The data backs this up completely. These charts show this incredibly clear trend. As we store more of the story in the cache, which is that horizontal axis, the amount of work the computer has to do, the cycles, the energy, the computations on the vertical axis, it just plummets. More memory means way less work.
And the numbers are really impressive. Let's put a number on it. For a decent-sized sequence of 512 words or tokens, using a full cache cuts the total number of computations by over 18%. That isn't a small tweak, that's a huge leap in efficiency. It's what makes something like real-time chat even possible.
Okay, so the magical scroll is a total game changer, but we can push this even further. What happens when our storyteller gets a whole team of assistants to help write different parts of the story even faster? Well, this is where the whole thing levels up and the optimization gets even more clever.
In a real AI model, these assistants are called attention heads, and each one is looking at the story from a slightly different angle. Maybe one focuses on grammar, another on character arcs, but they all need to know the context. So now you have a new problem, a logistics problem. How do they get that context? Do they each get their own private scroll, or is there a smarter way for them to share?
So you've basically got three ways to play this. First, there's multi-head attention, where every assistant gets their own private scroll. It's very thorough, but it uses a ton of resources. Then at the other extreme, you have multi-query attention, where the entire team shares one single master scroll. Super efficient, but maybe you lose some detail. And right in the middle, you've got grouped query attention, which is this smart compromise where assistants work in small teams and each team shares a scroll.
And once again, the numbers tell the story. Having fewer query groups, which in our analogy means more assistants sharing scrolls, it leads to these really big drops in both energy use and computations. Just look at the trend. As the number of groups goes from 16 all the way down to 1, the savings just keep getting bigger and bigger.
And get this. Moving all the way to that single shared scroll, the multi-query attention model, it cuts the required work by over 15% compared to the standard approach where everyone has their own. That's another huge efficiency gain right on top of the KV caching we already did.
And this isn't some fluke that only works in one specific setup. The research is super clear on this. Look at these graphs. It doesn't matter how many total assistants or attention heads the model has. Reducing the number of shared scrolls, the query groups, reliably makes the model more efficient. It is a clear, powerful, straight-up linear relationship.
Okay, storytellers, magical scrolls, teams of assistants, that's a lot of theory. So what? Why does any of this actually matter to you, the person just typing a question into an AI?
Oh, it means everything. These are not just tiny academic tweaks, they're the absolute bedrock of the AI you use every single day. They're the reason you get a response instantly instead of waiting minutes. They drastically cut down the massive energy footprint of data centers, which makes AI more sustainable. And maybe the most important thing of all, these efficiencies are what's making AI accessible to everyone, making it possible to run these powerful models on the phone in your pocket, not just on some billion-dollar supercomputer.
You know, the researchers behind this work, they put it perfectly. They said efficiency is not just a nice to have. It is the critical barrier. Without these kinds of optimizations, the AI revolution would still be stuck in a lab somewhere. Amazing in theory, but just too slow, too expensive, and way too power hungry for any of us to actually use.
So, the next time you get an instant answer from an AI, you'll know the story behind the speed. You'll know the tale of the forgetful king, the magical scroll, and the clever teamwork that makes it all happen. This is the race for efficiency, and it's a race that affects all of us. The big question now is, what comes next?